revealing secrets of the Earth and stars.
This will be the hottest place in the universe.
And blurring lines between minds and machines.
Wow, that is impressive.
Irish scientists have their fingers on the pulse.
This week on 10 Things to Know About, we're headed underground in search of buried treasure in the Earth's crust.
Meanwhile, Jonathan and Aoibhinn take to the skies to investigate a silent killer that lurks all around us.
The Earth's crust, a thin layer of rock laid down by volcanic activity. In relative terms, it's no thicker than an apple peel. Yet these rocks support life as we know it, providing the metals, minerals, building materials and energy resources on which society depends. This thin skin of our planet protects us from the dangers within. One such danger is radon, a naturally occurring radioactive gas that is formed in the rocks and soil across Ireland and present in the air we breathe. I'm meeting EPA radon expert David Fenton to discuss exactly what radon is and how harmful it is to our health.
We live in a radioactive world in the sense that radioactivity is quite natural. It exists within nature. We get radiation doses from the sun, we get radiation doses from outer space when we fly in aircraft and so on. Radon is a naturally occurring radioactive gas that has no colour, taste or smell, so your senses are blind to it. The radon is coming from radioactive elements that are in the ground called uranium and radium. And the problem with it is that as it's coming out naturally out of the ground, it can build up in people's houses, it can seep into houses and it can build up to high concentrations.
Is that something we need to be worried about in Ireland?
Well, radon gas in homes is linked to some 250 lung cancer cases each year. So it is something that people need to be concerned about.
Do we have examples of very high levels of radon in Irish houses already?
The highest one we found was in North Kerry of a house with 49,000 units of radon. Now, bearing in mind the safe level is below 200, this house had very, very high levels of radon in it. It's a tragic story because the householders unfortunately died of lung cancer, and one of the doctors who was treating them felt it was so unusual for two people non-smoking living in the same house to have lung cancer that he said to get the radon levels checked. And we found then this huge level of radon in the house.
Overexposure to radon gas can clearly have tragic consequences. And perhaps the most frustrating thing is that the health risks are surprisingly easy to minimise. It's something that RTE journalist Paul Cunningham has reported on many times.
I became interested when I was environment correspondent. I didn't know very much about it, so I wanted to find out more, and I looked up things like the World Health Organization, which told me that radon is akin to asbestos, akin to tobacco smoke. This is an absolute killer, and because we don't have any senses to it, we can't see it, taste it, hear it, you are effectively sitting at home in a cancer factory, which is going to deliver lung cancer to you unless you do something about it.
And this is something that we should really be acting on.
I think this is something which should have been acted on a long time ago. That's not being critical of those who are working on the ground, those people who have been looking at radon difficult areas, those people who have been trying to highlight the problem. They've been doing Trojan work. I think it's up at the policy level. I'll be honest here, I am simply shocked that this problem has not been eliminated in 2017, 15 years on when I first heard about it. We have things called BER, those building energy regulations. You can't buy a house, you can't rent a house unless you have a BER cert. We should have radon certs.
But without BER style certs, the only true way to know how much radon is in your home is to test it. You can buy test kits for about €50, and if the level of radon is found to be over 200 units, you should consider acting to prevent radon getting into your house.
It's quite a modest fee, we would hope, in order to reassure people what the radon levels are. I would always try and get people to treat radon like you do any other household hazard. Like, people are well used to putting smoke detectors in the house to protect them against fire, well used to getting their boiler serviced to protect them against carbon monoxide. And radon is just another one of those features in a house that you need to pay heed of. The most common method in Ireland of fixing high levels of radon is a thing called a radon sump, which is a small little cavity that's put under the house, dug out from under the house from the outside, and it is then using that sump, the radon is drawn into it and then it's exhausted safely to the outside by an action of a fan.
So it's like it's collecting the gas in one particular area that it can be removed from the house without seeping through under the floors.
Yeah, yeah.
The threat posed by radon gas cannot be underestimated. And I'm meeting Christine Keaney in County Galway, who's already taken steps to tackle the problem in her home. Christine, how did you find out about radon in your home?
It was really from my son-in-law when I was having the work done to the house. He said, Granny, I think, you should have your house tested for radon. He's from Austria and they're very up to date. So he got me information, got me literature, and I sent off for the test and did the test.
And did you know what radon gas was at the time?
No, I didn't really know.
Because you had really high levels of radon gas.
About 8 times the level advised. And that would be equal to 8 chest x-rays per day.
Every day?
Every day.
And that's not something you could ever notice yourself?
No. I had no idea at all.
That must have been quite frightening, actually.
It was frightening, it was.
On receipt of the test results and following advice from the EPA, Christine took action to protect her home. So Christine, this is what you have now on your roof, and that's taking the radon out from underneath the house.
Yeah, there's a sump inside in the hot press and there's a fan taking up through the house and out comes the chimney there. And then, of course, I had to test it again and it came down from 1600 to 200.
So you're now in the safe
I'm
zone.
a happy bunny.
Wonderful. That's
Yeah.
great.
Research efforts are being made to improve our understanding of the variance and concentration of radon levels across the country. The EPA and Geological Survey of Ireland are mapping entire regions of our island's crust, and the richness of this data puts Ireland amongst the top countries in the world for the quality, breadth and availability of geoscience information. The TELUS survey plane that maps radon levels is one of only a few of its kind in the world. It's been heavily modified for this exact purpose, and we're not actually allowed on board this survey aircraft as it comes under the same regulations as a test flight. But never one to pass up an opportunity for a panoramic bird's eye view.
So Jim, if we're studying rocks in the ground, why do we need to be able in an airplane?
Well, as you can see, we can survey all of the area and we can collect the data very quickly and very efficiently. Before each flight, the pilot will tell us where they're flying. So we plan the flight lines. So they have a series of these long linear lines. We fly up and down these lines. We also have to fly very low. So we're flying at about 60 meters.
Wow.
The closer we are to the ground, the better the instruments work.
Is that dangerous?
No, not dangerous. The pilots are very skilled. They've been doing this they have hundreds or probably thousands of hours of flight time. Weather is a big issue for us. And particularly it's a big issue for the flying because we can't fly when it's actually raining because it affects the instrumentation. And also from a health and safety point of view, we can't fly when the wind is too strong and also if it's too cloudy.
Do you ever get to do the flights? How long does it take to do this project?
It can take quite a while. So we try and fly during the summer when the weather is better.
Sometimes.
Sometimes, yeah.
But for today, we're looking at a gas. How do you search for radon gas?
Well, one of the instruments on the aircraft we're using measures natural radiation. And radon is actually a decay product of uranium. So we have a gamma ray spectrometer in the back of the aircraft. And effectively, this is a sodium iodine crystal. And as gamma rays are emitted from the ground, from the rocks and the soils, they pass through this crystal and leave a little flash. And we count these flashes. And the more flashes we have, the higher the count. And the different energy of these flashes tells us what the element it came from.
So that's the radiation rather than the gas itself?
Exactly, yeah. So we determine the radiation, and we then can determine the uranium content in this case, and therefore we can work out where the radon gas is coming from.
Presumably then that would give us a good map of high-risk areas for radon gas that we can concentrate our efforts on.
Yes and no, it's not quite that simple. Sometimes it's coming from the source and then it's moving through the soils and the rocks to a different place in the surface. So understanding how it does that gives us our final product of where the radon gas is going to be coming at the surface.
So the layers of Earth above that uranium are really important to figure out where the radon is going to come out.
Exactly.
You can access the EPA and GSI radon maps online to find out whether your home is in a high-risk area. Alongside improved mapping, Dr. Mark Foley and his team at NUI Galway are looking at how radon is getting into our homes in the first place.
The way we live nowadays, we like our warm, cosy houses, so the temperature inside a house is much warmer generally than the temperature outside, so that means your house almost acts like a hoover and sucks the radon gas up from the ground. An important part of this research is to actually look at the size of these stones and how the size distribution of these stones affects the actual ability to suck the air out through this foundation, because that's critical. If you want to reduce the radon levels in homes in Ireland, you need to be able to suck the air out from this foundation and vent it outside the house. We can, through this research, optimize how the house is built so that we have optimum building materials to go underneath the foundation of a house. If your particle size is very large, you will have easy airflow, whereas this very fine material and moist, when you have wet material like this, it's going to be very difficult to extract the air. So you can see my researchers here compacting the stones, and we place these in this test setup and blow air through. They're compacted because this is typically what you'd find in a house. Before you build your house, you'd compact the material before you pour your concrete, because obviously that would affect the structure or the subfloor of your house.
Mark is collaborating with researchers in Spain, and the results will inform building regulations and European safety standards to reduce the amount of radon entering our homes.
In a European perspective, we would be among the leaders in radon technology as regards looking at the optimal specifications for radon prevention and radon remediation.
Through movies like Jurassic Park, we've heard of the age of the dinosaurs, a time when a particular group of animals ruled the land. With humans now dominating almost all aspects of our planet, many scientists have declared that we are now in the Anthropocene epoch, or the age of humans. The great history book of our planet is written in stone, with different layers of rock corresponding to different chapters, which can be read by geologists. So when exactly should the Anthropocene begin? Well, so far there are a few candidates. A layer of radioactive elements left in the rock from nuclear bomb tests, or a thin plane of plastic left behind by wasteful humans. But it turns out that humanity's signature in the rock may not be human after all. Instead, our legacy might actually be chicken. Yes, chicken. This is because the start of a new geological age is usually clear in the rock due to the widespread appearance of a characteristic fossil which hadn't been seen before. With a whopping 60 billion chickens being eaten every year, their bones are being fossilized in landfills, leading to a distinct layer of avian evidence in the rock. And chicken bones might even be the ideal candidate. Our insatiable appetite for chickens across all cultures is causing their bones to be preserved from Australia to Asia to Ireland, giving a consistent global coverage to the layer, easy for future geologists to spot. So despite ending up on the dinner table, the domestic chicken looks set to be granted immortality. See you next time.
In part one, Aoibhinn and Jonathan investigated the potential harmful gas radon, but the Earth's crust is full of wonders, like raw materials, which we can mine and exploit.
Copper was one of the first metals ever extracted and used by humans thousands of years ago. Because it conducts heat and electricity so well, copper has become absolutely central to modern living, from laptops and phones to cars and homes. But with increasing concerns over the environmental impacts of mining, scientists worldwide are looking at ways to locate and recover copper in a more efficient and eco-friendly way. Some of the answers could be found here, in this abandoned copper mine in Aoibhinn in West Cork.
This is a fantastic place to study geology. There's an amazing outcrop. We can see that here behind us. And here in particular, we have a concentration of copper ore. And it is that concentration of ore that attracts us here, because we're all about understanding the processes that produced or concentrated the ore at this particular location.
Dr. Richard Unit, who's been working as a geologist for more than 30 years, has kindly agreed to take me into the copper mines to tell me more.
Richard, this copper mine is amazing. Tell me its history.
Well, we're in what's called the mountain mine at the moment. Mining started here in about 1812, down on the coast. It wasn't until a few years later that they discovered this area here, and they mined here up until about 1894, when major production stopped. In that time, they mined, it's been calculated, about 1 million tons of ore.
Wow. And how do you actually mine copper?
Okay, they would have identified where these quartz veins that contained the ore minerals were, and using hand tools plus explosives, they would have blasted their way through the rock. And what you actually see here in the mine around us is what's known as a stope. They actually followed the vein. So this shape that we've got here, this cavern that we're in, is where the miners have followed the vein down through the rock.
Okay, so this was full of quartz and they excavated it all out.
Absolutely, yes.
Can you see copper still in the mine?
Yeah, you can see it as green and blue stains on the walls all around us.
Yeah, it's stunning. But that's not copper itself, is it?
It is a mineral of copper. These are what we call secondary coppers. They're what's left behind when the copper weathers out. Mining in Ireland has a very long history. So we're going back to 2400 BC, when on Ross Island in County Kerry, they were mining out the copper and making copper implements. They've actually renamed that particular period at around 2400 BC, the Chalcolithic. Chalco standing for copper.
Wow, so 2,000 years ago, copper was a big industry.
4,000 years
4,000 years ago. My sums are all
Yeah.
out. Wow, that's incredible. And where does your research fit into all of this?
Okay, what we're doing here is we're doing an integrated approach. So we're using old school and new types of technologies so that we can understand better how copper deposits form. We're using classic geology, we're doing mapping, we're looking at the structures, we're going underground, we're taking samples of the rocks themselves, but we're also using drones on the surface. So we're looking at the area to see how the veins cut across the countryside, and we're developing three-dimensional models, which we not just get the surface that we've got above us, but also we can see underground. So we get a better idea of the shape of these types of copper deposits.
So you're getting a complete picture.
That's correct.
Along with Richard's underground work, drone technology is being used to allow researchers to build extremely detailed pictures from the air.
The drone has a camera gimbal with a 4K camera attached, and I look straight down and I make pictures every second. So I form a grid over the area, which gives later on a very good aerial image. We have satellite images, but we need a more precise image.
So you're basically doing a painstaking visual survey of the landscape, bit by bit by bit.
Yeah, exactly.
Were you a drone geek who kind of went, oh, how can I use a drone in my research?
Yeah, I'm a geology geek, but I was here doing my mapping fieldwork, writing everything down, having a GPS handheld with you. And I thought, okay, if I get a high resolution map of the complete area using a drone, that would be amazing.
So by being a geology geek, you became a drone geek?
Exactly, yeah.
Using this high-resolution imaging, Jürgen can map the location and orientation of the white lines of quartz veins which host the copper. Combined with satellite imaging and structural details of the underground layout, Jürgen and his colleague Kuhn can create an amazing 3D model of the entire mining area.
You can actually see it in perspective as well as what's in the subsurface. You can see all those tunnels, and it really gives you a sense of scale, how deep these miners went, over 400 meters deep.
So that's the edit where we went into that mine, into the underground. Yeah. And the big lake is over there where the green line is continuing. That's called the north-south lode.
It's astonishing how, we've only touched upon the surface, but it goes so deep down there.
Yeah.
It's just incredible.
While researchers are embracing these new visual technologies, purists will be happy to know there's still a place for the old hammer and chisel techniques. While we were in the mine, Richard took the opportunity to collect samples of the quartz vein material containing copper for further analysis.
In this case, on the microscope, you can see the golden colour on the left-hand side, which is the copper metal, and the grey colour on the right-hand side is the quartz. Inside this quartz crystal, we have these very, very small shapes that you can see. And what these are the remnants of the fluids that carried the metal and the quartz and deposited them in the veins that we see. And amazingly enough, these, at a minimum of 270 million years old, are still moving today. What we can do with these fluid inclusions is we can do what we call heating and freezing experiments. So we can heat them up so that bubble eventually amalgamates with the fluid that's also in this, so it basically disappears, and that is the minimum temperature at which these veins formed. The reason we need to know the sort of temperatures and maybe even the composition of the fluids that were involved is that maybe we're looking in other areas in Ireland or in other countries where we just have quartz veins. But if we can get the kind of information that we know about these, we can say, well, perhaps there may be copper associated with these veins somewhere.
With the amount of copper required to satisfy our modern lives increasing all the time, the quest to locate new sources adds to the environmental concerns over methods of mining. There is certainly a need for the materials, but we need to extract them in a more environmentally responsible way.
Your research will be able to pinpoint more efficient and precise ways of finding good copper rather than maybe the kind of blanket excavations.
Yes, that is the hope. So in other countries, say in South America, where the majority of copper comes from now, say in Chile, the deposits they're looking at there contain maybe 0.5% of copper. It's quite an inefficient way to mine. They use a lot of energy. They have a big carbon footprint. The kind of deposits we're looking at here may have 3, 4, 5% copper, which makes them more economical and more efficient to mine.
Very good.
We're researchers, we're interested in process, and when we understand the process here, this allows us then to take that model, these concepts, and take them to other sites across the country.
That's our 10 things to know about the Earth's crust. Next week we look at incredible advances in brain technologies.